the most important or the second most important, depending on your taste, quantum algorithms discovered so far, which is the so-called Grover algorithm. Now, this is arguably the most important or the second most important, depending on your taste. As I said, the Grover is, provide just a quadratic speed up, but it is potentially applicable to a plethora of problems of interest. Another one is the famous Shor algorithm that produce an exponential speed up, so much better, but it is applicable to a more restricted set of problems. So depending a little bit how you feel, you can prefer one or the other, but they are both great. So let's see, first of all, the problem. So as usual, we have n equal to 2 to the n, right? And we are given with a certain, let's say, as usual, what happened? Oh, no, yeah. As usual, a certain input, x, that we write x0, x n, minus 1, where, as usual, xi belong to 0, 1. And the idea is that we want to find, so let's say the goal, find I such that xi is equal to 1, if existent. Could be that there are no such things. It could be that there might be 1, might be 2, might be some function of n, and so on. But the idea is to find what people call a marked spot in this database. So you see that the applicability of this is enormous. I mean, essentially, anytime you have to search in a database something, having a quantum algorithm that do this thing very well could potentially provide huge advantages. So this is why this algorithm is so famous. So let's start with the classical complexity. So first, classical. And here, we can provide both a no and an omega. So we can provide both an upper bound and a lower bound to this problem. And what do you think? What is an upper bound on this problem? O? N. And the lower bound is as well omega n. So classically, there is not much fantasy in what we can do. Yeah. One is an upper bound, another is a lower bound. So you need at least n queries, and you need at most n queries. So, so classically, there is not much that we can do. We can just start to explore the database and patiently look, and after n queries, we will know if and where there is a marked spot. So our idea now would be to improve this performance using quantum mechanics as usual. Good. Okay, so let me start with the definition. So we define T being the, let's say, the number of I such that xi is equal to 1. People more, let's say, well-educated than me will call this guy the, what is the name? Yes, Hamming weight of the string. So the string has as many 1 as given by T. And here we, today, for all the time, we will assume that we know somebody told us T. So we know how many solutions there are, at least at the level, if you want, of order of magnitude. There are, if you want, the algorithm become immediately much more complicated if you don't know T, as we will see. And there are ways to, let's say, to tweak the algorithm to work also in case t is unknown, but they are more complicated, and so we will restrict to this case. Now, let's define also the Grover, let's say, operator. I mean, it's a combination of things, and we will, let's say, explore it, each part. But let's define first, let's say, a black box that we call the Grover operator, and we call it curly G. And this guy is the following beast. So G, by the way, I mean, triviality. Since we have this guy, this algorithm will work with n qubits, small n. We have a question. No, any, whatever, yeah. Okay, so G is given by this beast. So the usual Hadamard fold stuff. Then we put R naught, that I'm going to define in a moment. And then our beloved. So let's define this. So, okay, this doesn't require a definition. This doesn't require a definition, right? So let's define these two objects. Well, OX plus minus, we know very well what it is, right? We have our, let's say, address I, and okay, I write, and then somebody tell me something. Here there is a little bit of mistake, right, as usual. I'm assuming that there is an ancilla qubit that starts in states minus, and it is used to convert the standard query to the phase query. Do you remember this point? Yes, okay. So this is just a phase query that go and check on the database if the address is pointing towards a point having 1 or 0, right? And then we have the other ingredient is R0, which is the following operation. So R0, when act on 0 to the power of n, gives plus 0 to the power of n. And R0, when acting over any other state different from 0 to the power of n, gives minus 0 to the power of n. So it put a minus sign whenever this guy it's different from 0 to the power of n. Now, about this operation, there are two ways to implement it. One smart, one dumb. Somebody wants to make a proposal? I mean, the dumb is fine. Then we fix it. There is nothing personal about that. So, yeah. Okay. Oh, sorry. Thanks. Okay, very good point. Otherwise, wasn't unitary. It's minus I. Put a minus sign in front. Thanks. Okay. Proposals? Okay. So the dumb way would be, in principle, to create an extra register, right, in which you put 0, 1, 1, 1, 1, 1, 1, 1, and then you do another phase query to this extra register, such that whenever you point somewhere else that is not 0, 0, 0, 0, you plug a minus sign. This is dumb. The smart way is it's dumb because essentially you have to build an extra register of dimension n, which an extra input of dimension n, and then you have to access this with some Boolean function that probably require a certain number of gates. So it's dumb in the sense that make, let's say, the complexity higher. So I don't recommend that. The smart way is actually contained, is a small variation of problem, let me see. Now I don't find it. Yeah, problem 6, a property of Toffoli. A property of Toffoli was essentially doing this thing, was just asking when you get 0 to the power of n to do 1 minus this. It's not hard to change this circuit a little bit and implement that. Anyway, so let's say that these two operations now are well defined, at least. We have a way to implement them. So now let's see the full circuit. So this is just part. Now the full circuit is the following. As usual, we start with our n qubits, all in states 0. Then we put a set of H's of Hadamard. If you want not to be confused with this Hadamard entering here, they're on top of that. And then we start to operate with our black box G many times. And we do it k times with the k that we will fix in a moment. We will discuss in a moment. After that, you do this operation k times. You do a measure in the computational basis. And the claim that we're going to discuss and show and comment and so on in a moment is that this operation, if k is well tuned, with high probability, will give us a state I such that xi is equal to 1. And, okay, another thing that I forgot to mention. This guy, what is the complexity of this guy in terms of query complexity? How many queries I do for each guy? Who said 1? Good. So this guy has query complexity 1. So this algorithm in total will have OK. So the big question, which we will arrive towards the end of the lecture, is to decide if this OK is smaller than ON. Otherwise, no reason to do anything quantum. Good. Say again? As I said, okay, let's do it again. So the goal is to find an I such that xi is equal to 1. Now, suppose that somebody, probably the guy that built the database, gave you the information that you have a certain number of ones, t, but you don't know where they are. The goal is to find one of them. Now, the claim is that applying this circuit, so applying first a fold of Hadamard gates, and then start to apply k times the Grover box, this guy, the claim is that when you finish to apply the k time and you measure, so as usual, after this, your state psi can be written as a summation for, let's say, I going from 0 to all the time, n minus 1, alpha I, right? And we know that the probability of extracting, and when we do a measurement, we collapse to certain I star, which is random, but with probability alpha I star square. The claim is that after doing this, if we tune properly K in a way that we will discuss in a moment, the claim is that with extremely high probability, we will end up on an I star that is pointing toward a location where there is a 1. As I said, I asked what is the query complexity of this algorithm. The query complexity is 1 for each grover. We apply the grover k time, so the complexity is of order, or if you want an upper bound over the complexity, is OK. And the hope is that we can show that this OK is parametrically smaller than ON. Clear for everybody? Because classically we have ON. Do we have T? We assume that we have T. And in K, there will be a T dependence. Yeah. This is N capital. This is N capital. It's correct, no? Right? You have a database with N entries, capital N, that you parameterize with small n qubits. Is the usual thing, right? If you have I living in 0, 1 to the power of n, you can index 2 to the n different values. Yes. No. Okay, good point. The question is the following. After this, no, I'm not sure I got the question. So I repeat what we get, and then you tell me if I answer it. So after applying the Grover k times, we will have, of course, a superposition, which will include both the I's, which are, let's say, bad, which are pointing toward places where you have 0, and the I's that are pointing towards places where you have high. Now, the claim is that the probability, so if you want, okay, let's be more explicit. After this, our psi, let's say, initial is 1 over square root of 2 to the power of n, let's say, I. So the probability, if you do a measurement now, the probability to end up in a state that is pointing, it's the same for anything. And so suppose that you have just few slots, suppose that T is very small, the probability that by random choice you end up in the, it's super small. The claim is that in doing this, we will move from a situation like this to a situation in which the alpha I are very unbalanced, and they are highly concentrated on the states, on all the states that are pointing to the right direction. So when we will do a measurement, we will end up in one of those. We don't know which, but in any case, the problem will be solved because we will find a location where we will find the I. Does it answer? Good. Other? Yeah. Yes, it's the same, but if you want this guy written here is like OX, H. So if you want, this is an extra thing. It's not included in a Grover thing, but they are exactly the same. No, right? Because I have the Adamard, then I enter in the Grover, and in the Grover, the first thing I see is the OX plus. So your question was, are you essentially applying identity because you have Adamard and Adamard? No, because in the middle there is OX plus. You know, Written in this way means that in the circuit is the other way around. The first that act on the state is this, and the last is this. Other? Yes? Correct. We will see that in very high detail. But the idea is that the grover start to move amplitudes from here to the states where you want. Which one? Here? Yes? Of course. Same. No, they are still all possible. I'm just claiming that the alpha I for I pointing to the wrong places are very suppressed, and the alpha I for I pointing to the right places are highly amplified. So I'm not cheating. It's not that I restricting the sum somewhere. It's just that, let's say the physics of the circuit is going to move the amplitudes from the wrong places to the right places. Of course. No, no. Each xi is just 0, 1. So you have 0, 1, whatever, another 0, 1, another 0, 1, another 0, 1, up to this. You have repetition. This is a string of bits. Yes, yeah, this notation is probably confusing. Let's say that you have a vector with x0, x1, x2, and so on, and each of them can be either 0 or 1, and is given by somebody. You want to search inside, and you want to find a location in which you have a 1. Just because we want to use qubits to address them, and so if it is not a power of 2, you have to partially use some qubit and so on. Okay. So now, essentially, what we have to do is to show what all of you essentially already anticipated, that our goal is to move the amplitudes from the bad to the good places, which is not that hard, if you know how to do it. Okay. Okay, so we have that state. So let me remind, let's give a name to the initial state. So this guy that I was calling psi initial, let's be more precise, and let's try, not more precise. Let's give a name that we will use later. We call it U, like uniform, and this becomes 1 over square root of capital N, summation over I. Isn't the same? Yeah, okay, yeah. Okay, now, definition, let's define two states, one that we call G and one that we call B, like a good and bad, okay? And we call the good state, so remember, we have T, good states, and then minus T, bad states. So we define G to be 1 over square root of T, summation over all the I such that xi is equal to 1. So these are the good states, I. So we define a uniform superposition of all the states that we want to target. And similarly, we define B as 1 over square root of T, n minus T, summation over all the I such that xi is equal to 0 of the I. So these are the good and the bad. Now, okay, so now the next point is to rewrite U in terms of these two guys. And here, really, a simple algebra show that we can say that U is equal to square root of T over N G plus square root of N minus T divided by N bed. This is a super simple algebra. Okay. Now, properties. Because it's the number of states, right? How many states do we have here? Capital N. Or to the, I apologize for the confusion. I sometimes use 2 to the N and sometimes capital N. But I wrote there that they are the same. Yeah, I should probably be more to avoid confusions, but exactly, power of small n. Yes. So these are, let's say, computational states, right? So they are, let's say, strings of 0 and 1 for small n slots that, let's say, they are all the addresses in this large database. So what is other points? Okay. What is this? 1. What is this? What is this? Perfect. So we have, let's say, in a very simple way, we have obtained that U can be written as a linear combination of 2 cats that are orthogonal to each other. And it's also very easy to observe. I mean, by definition, it's clear that these 2 numbers are both smaller than 1, and the sum of the square of those sum to 1. So we can parameterize then in the, so let's say equal to sine of theta G plus cosine of theta bed, with theta being the arc sine of square root of t over n. I mean, this is just rephrasing things in a different way, but it's exactly the same thing. Good. So we can say that we have already, and this will be the crux of all the algorithm, if you want, we can say that our U is living on a 2-dimensional plane, right? Where, let me avoid mistakes, yes. Here, a vector 1 here is, I call it, let's say, I define it to be B. Here, I define this guy to be G, and they are orthogonal. And given that I have a sine here, a cosine here, I have my U that is here, and this is my theta. So the idea is that we want to make an evolution such that this guy, this theta, will move toward this direction. When this theta will be exactly in this position, we will have probability 1 to extract only a good state. Can you repeat? It's not me, it's Grover. Yeah. Yes, Grover is very smart, yes. Okay, let's see. So the claim now is simplified to say that this G is essentially realizing a movement in this direction. And we keep applying until we got as good as possible a line with the good state. Good. Now, the next ingredient to show that this is the property is to introduce a very small, very simple notion, which is reflections through subspace. So let's assume that we have a certain, let's say, subspace. So we have, let's say, a vector space, and we have a subspace that we call V, and we have an operator that we call O, and we say that O is a reflection through through V if O acting on V gives V if V belong to V, so does nothing on the states that belong to this space, and OW is equal to minus W if W is orthogonal to V. So if the state is orthogonal to the subspace that I want to reflect through, I get a minus sign. This is a reflection. Now, claim X, OX plus minus is a reflection let's say, I mean, here we should be more precise. In the subspace generated by G and B, okay, in that subspace, OX plus minus is a reflection through B. Is it clear, this statement? No. Okay, good. Remember what is this guy. OX plus minus is a phase query that put -1 if the state is good, and put +1 if the state is bad. So is exactly this property. As I said, actually this is a this is a reflection over, if you want, the span over all the I such that xi is equal to 1. So in principle, is a reflection over this vector space. But when you, let's say, restrict to the subspace generated by these two guys, this is actually a reflection over B. So this, now, by the way, sorry. Suppose that you have this property. Do we all agree that O can be written as 2 the projector over V minus identity? This is really a triviality, right? This guy, the projector over V, project over the subspace V, and then multiply by 2, and then I subtract the original vector. So if I were in V, I get 2 minus 1, 1. If I were outside of V, I get 0 minus 1, minus 1. So, okay, now, next claim, a little bit more tedious, but not that much, is that H is a reflection through U. Let's see how somebody already have an idea how to show this property? Yeah, please. the minus sign. Yes, which is this property, right? No, sorry, when it finds the good state. Indeed, the reflection is defined such that you do nothing on the space where you are reflecting through, and you put minus sign over the orthogonal. So to be a reflection over B, you have to do nothing over B, and do the minus sign over the orthogonal of B, which is G. Questions, comments? No, we are going to show that. I'm just wondering if somebody want to try, otherwise I go through. Nobody is so brave, so let's try. So this guy can be written to Do we all agree on this property? Putting nothing in front of this and putting minus in front of everything else is exactly the same of writing in this way. Good. What is this guy? UU. What is this guy? The identity. So this is a reflection through U by this property. We are projecting over U, multiplied by 2, and then subtracting 1. Good. So we have proven that what the Grover is doing is essentially two reflections, one after the other. Now let's see why this solves our problem. Let's go here. I first do a reflection over B. What I'm going to do? Right? Then, once I'm here, I do a reflection over U. So, if you want, GU is now this guy. So we see that we've been closer to the states that we're looking for. Good. So now it's just a matter of doing a little bit of algebra and see that see what we get after k iteration of this game. Questions, comments, complaints? Good. Oh, well, everything is in the note, eh? Okay. Okay, so now let's assume that we did k iterations of this beast. So our psi k, so the psi after k iterations, this is really a simple bit of algebra, become the sine of 2k plus 1 theta, good, plus cos 2k plus 1 theta. Bad. So now we can ask what is the probability of success after k iteration. This is simply sine square 2k plus 1 theta, right? So, what is the best k, which we denote with k tilde? Well, not so hard. We have to repeat. No, say. I mean, this beast must be equal to pi over 2. So we have to solve 2k tilde plus 1 theta equal to pi over 2. Simple algebra, and we get, so that, let's say, this gives us k tilde equal to pi over 4 theta minus 1 over 2. Let's replace now this guy. This becomes pi over 4, what was? Arc sine, and this is the crucial step, square root of t over n minus 1 over 2. Now let's assume that t was parametrically smaller than n, so t over n is very close to 0. Notice that this is not a joke. If t was large, comparable to n, was way better to go straight with the classical algorithm, because with finite probability, after few iterations, we will find. So the only situation, the only, let's say, regime in which the quantum algorithm can be of any use is when t, if you want, when t is O n 1 minus alpha, okay, when it is suppressed. Because otherwise, if it is of order n, you have finite probability, you just check, and after few iterations, not few iterations, few classical searches, you will find what you want. But suppose that you have your Spotify box and you are looking for a specific song, that can be nasty, right? Good, so the arc sine in the regime that we care can be approximated with t over n, right? And so overall, we get that k tilde is, let's say, is O square root of n. And so we see a quadratic speed up. If t is, well, depends, of course, but if t it's, well, let's be more precise, square root of n over t. So we beat the classical case. The classical case was O n. So we have a quadratic speed up with respect to the classical algorithm. Questions, comments? T must be subleading in n. So any power that is, let's say, I mean, can be whatever you want, but suppose that this is On, then in principle you could say, oh, amazing, this is of order 1. But at the same time, also the classical one will be of order 1. So it's not really amazing, right? So let's say to make sense, to start to thinking about the quantum algorithm, I believe you have to think that your t is subleading in n, and then you get a speed up. Well, it's algebra, right? Let's say the idea is that let's do at the first iteration. So after the first iteration, the angle is now 2 theta plus theta, so 3 theta. And then you keep doing. Okay, now to conclude the lecture, I want to spot one, if you want, one loophole, or I mean, one problem. I mean, as I said, the main problem is suppose that you don't know T. Okay, yeah, first, no, sorry, yeah. What? No, why all the entries that returns what? Suppose that you have just one spot and you don't know where it is. You have to query n times in order to find the thing that you want. Okay, we have to be more precise. To have a finite probability to find the spot, you have to query you have to query at least on order n times. Because suppose that you are so unlucky that you keep, and well, it's not so much unlucky, because if you have 1 over n and then it's very large, you have to query almost n times in order to have a finite probability to find, right? So you have to, so here we are counting the comparison in complexity in terms of how many times you have to go to your oracle and ask. Classically, you have to do an order n times in order to have a finite probability to find what you are looking for. Here, you do it, this oracle query, only a square root of n times. Okay, good point. If you want to spot all of them, essentially, I mean, roughly speaking, the complexity will become O t square root of n. Roughly speaking, you have to run t times the Grover algorithm, and so roughly speaking, the complexity becomes that. Yes, as I said, repeat. No, because the value of t is how many ones you have, but you don't know where you are. So to find one, you have to randomly investigate, right? Suppose that you want to find one among 4 songs that you like, but you don't know where you are. If there is no an ordering, okay, in principle, suppose that you can, okay, this is just 0 and 1, so you have no ordering. But suppose that you can order, or your input is ordered, then things become way more convenient, let's say. But if there is no ordering, nothing, you have no other clue than just randomly check. So become probably, let's say, n over t, let's say. But still, t is subleading in n, so, and in any case, also here, you have a square root of n over t, so.
But just first, because of this question, but it's true that if you are very lucky, with t measurements, you might get, I don't know what the definition of this omega is.
The omega is the minimum number of queries to make the probability of success finite, not dependent on n.
There is a probability.
Yeah. No, agree. Same. The point is that probably you have to dress this oracle with something that become f of xi.
But then you explain with this Tifoli.
Yeah. You can do it.
So
I mean,
it's called the search algorithm, right?
yes.
Normally I would have words, and I know that.
Absolutely. That's it? Okay. Related to what Pedro was asking at the very beginning, of course, this can be also, let's say, generalized to the case in which this is not a bit, but it is a word. Let's say it's a number. Let's say it's an integer number. Then you have to encode these numbers in bits, and you do a query that is not, let's say here you have probably something like, let's say, okay, I have to decide, but let's say, for sure you can do a standard query, so you can do xi. This you can definitely do, and you put here, instead of one bit, one simple qubit, you put b qubits, how many bits you need for this. And then probably this instead cannot be done, so probably you have to do the algorithm with the standard query rather than the phase one. But or you can, I would say, yeah, or you have to modify the algorithm, but can be done. I mean, depending on what you are doing specifically, can be done. Like, for
but imagine I have a sequence of words, and I want to count how many have an odd number of vowels.
Yes, you encode that in a Boolean function, become exactly the same. Yes.
I just have words, I have
Absolutely. Absolutely.
and then
Absolutely. 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 Yes. Instead, suppose that you want to find the word apple, then you have to encode a function that given f of x gives, let's say, 0 if x is different than apple, 1 if x is equal to apple, and you go. Yes. Okay. Now, how much time do we have?
you can go over time.
Okay. Ale. But yeah. Well, when you are, you can, I mean, when you are tired, you can leave, let's say. Ah, they cannot. Okay, you cannot. Okay, now somebody should raise a complaint here. K, in which, how mathematician call that? In which field is living K? It's an integer, right? K is an integer. K is the number of times that you apply the Grover. It's an integer, right? You cannot apply 3.2 times. Now, this K tilde, good luck to be an integer, right? Could be whatever. So, what can you do? Okay. In principle, you can say, well, again, my life doesn't depend on this, so I'm satisfied with close to 1 probability, so I go, instead of going directly to K tilde, that is impossible, I go to some K bar that is close enough to K tilde. But that is, suppose that really, I mean, the word depend on this result, you don't accept a finite probability of disaster, and so what can you do? In principle, nothing, but we are going to see that you can do something. And you can, let's say, tweak the game a little bit in order to make the thing work with probability 1 also in that case, also when K tilde is not an integer. The other thing, much more complicated, and we are not going to cover it, is what you can do if you don't know T. Because if you want the decision of how many queries or how many Grover to do is determined by T. And notice also that if you overshoot, your probability starts to go down again. So it's very risky. Doing things blindly can be extremely risky. Like after iteration, you start to go down. This is a complicated problem as far as I understand. And there are, let's say, essentially the idea is that you have to, let's say, scan starting from small k to large k until you find an optimal k, and there are ways to tweak the algorithm in order to work also in that case. But I'm not going to cover that. What I'm going to cover is the simplest situation in which you know T, and you know that this leads to a K tilde that is not an integer, so you cannot reach with probability 1, but nevertheless you can do something. So let's consider a particular case to make things easier. So we have, again, x equal to x0, xn minus 1. And we know that t is equal to 1. So there is just one solution to the problem. So let's call, let's say, I bar the only the only I that satisfies the algorithm. So we have this situation. Now, okay, so after k iteration, pk, sorry, let's say that, no, let's do more simply. Let's say that we find a k tilde, we know k tilde is pi over 4 arc sine square root of 1 over n minus 1 over 2, right? The best thing, and suppose that this is not an integer. Okay, so the best, for the moment, the best you can do is to define a k bar that you decide to be k tilde plus epsilon, with epsilon, let's say, in belonging to 0 and 1. So you say, I go to the next integer above k tilde. So epsilon is a number that goes from 0 to 1 and parameterize the error that I do. So for this, again, doing a little bit of exercise, you find that p k bar, again, putting in pk k bar and remembering that k tilde is this, so it's very simple. Pk bar, so the probability of success with that k bar, is equal to the cosine square of 2 epsilon, the arc sine of square root of 1 over n. So if you want, it's very close to 1. If you Taylor expand this, assuming epsilon is small, 1 over n is small, so it's very close to 1. It goes like probably like 1 minus epsilon to the 4, something like that, I would say. So it's very close, but it's not exactly 1. But as I said, we want to make pk bar, so our goal is to make pk bar strictly equal to 1. Nothing different than that. Is the integer above k tilde. So we do one iteration more than the point epsilon iteration more than the optimal. No, it's algebra, because you get a sine square of pi over 2 minus, and then you convert the sine square to the cos square. Yeah, if you do the computation, it's trivial. Okay, so the way to do that is to add a new qubit. So we now work with n plus 1 qubits. And in general, our addresses become j equal to j1 or j0. Okay, I'm using, the probability that I do mistakes is very high, so let me use 1 to n. Is like 0 n minus 1. And then I put j n plus 1. And then, so to say, define, so these are the new addresses. And then I define, let's say, a new input that I call yj, which is defined in this way, is 1 if j1, jn, so the address up to here is equal to I bar. So if I'm pointing to the only solution that I have, and jn plus 1 is equal to 0. And 0 elsewhere, otherwise. So notice that this is just a definition. I'm not really creating another database. I'm just, let's say, defining on the air a new database in which essentially I put the old database every time that jn plus 1 is 1, and I define that all the other possibilities are always 0. Now, question, can I implement the following query as that given j, give me minus 1 yj j by using the standard query OX that given I and let's say what I was doing. Yes, I and B give me I xi plus B. So can I use the old query that I already implement to implement this larger query without the necessity of building a new database and so on? The answer is yes. And it's beautiful. Here we have our query, OX. Here we put n j's, so the jn. Here I put the jn plus 1, which I treat as the control, or if you want, as the extra qubit for the standard query. And then I claim, and I do the following. Here I put an X gate. Here I put an Hadamard gate. Here I enter. Here I enter. I do this square, the standard query, using, as I said, this guy as this. So let's say that this is our B. I exit, 3, 5. And here I put another Hadamard and another X. Now let's see what happened. Suppose that jn plus 1 is 0. So we start from 0, become 1, here, become minus, enters here, and we know that when this guy is minus, what I'm doing is actually a phase query. So I do this, I exit, come back with the Hadamard, to 1, come back to 0. So I really implemented this query using this. Now, the other possibility, I start from 1. So I implemented, if you want, half of this query. I implemented this part. Let's see if I can do this as well. I start with 1, which is here, become 0, become plus, and here last time we were joking that doing a query with a plus is doing nothing, and we were saying, oh, come on, you do a query without doing nothing. He's playing his role. He's doing nothing, so I get nothing. I simply pass, and this go back to 0 and go back to 1. So I've shown in this way that what I'm doing is really the phase query that I was looking around, without inventing anything new, just using properly the extra qubit. Now, last step. Let's consider now this operation, A, which is h to the power of n, a rotation with parameter gamma, so cos gamma minus probably sin gamma, cos gamma. Now, this guy, when I do A over 0 n plus 1, what I get is a state that, without too much fantasy, I call U tilde. And this state can be written as 1 over square root of n summation I, vabbè, summation over I we know, no, better to say because I belonging to 0, 1 to the power of n, I, tensor sin gamma 1 plus, same thing here, 1 over square root of n, summation over I, now I don't repeat because it's clear where it is, tensor cos gamma 0 for the last qubit. Now, what is the probability to get the right state, which means a state that is pointing to the right spot? It's here. And so the probability is 1 over n cos square of gamma. So we see, you remember at the beginning, the probability, before doing the Grover, the probability of getting the right one was 1 over n. Now we start to see the magic. We can tweak the probability with an extra real parameter that is cos square gamma, that is controlled by the extra gate. Now, making things a little bit more, let's say, explicit, what you can do next, here I think I don't need anything anymore. I-bar is the position of the best, of the only spot where you want to go. Now, you can play a little bit with this game, and you end up with, okay, we define, where it is, sorry. Let's go here, yes. So, you can rewrite the U tilde as, I write in full glory, although it's not much nice, n minus cos square gamma divided by n, which I will later, I mean, this is square root of 1 minus p. And here I put an horrible beast, that is sin gamma square root n minus cos square gamma summation over all the possible I between 0, 1 to the power of n, I1 plus cos gamma n minus cos square gamma summation over all the I different than I bar I0 plus square root of cos square gamma divided by n I bar 0. And now I call this guy 1 minus p, this guy p, this guy is actually taking all the bad states, and it is normalized. This guy is the good state, and it is normalized. And they nicely satisfy our beloved property, BG equal to 0. So they are orthogonal. So I have once again the two-dimensional picture. I have once again a new theta that this time has been tweaked a little bit by this cos square gamma. So I can do exactly the same procedure as before, in which I replace OX plus minus with our SY. I replace h to the power of n R0, h to the power of n that was implementing the reflection through U. I replace it with A R0, A, I think this is a real operation. I have to check. Well, who cares? Probably there is an A dagger, I think. Anyway. Yeah, I think there is an A dagger, but it's not that important. But this realizes the reflection through U tilde. And so I have a new Grover algorithm with a probability that has been reduced a little bit. I can now run not K tilde, but the K bar that I wisely canceled, that was slightly larger than. I get an equation for gamma, so I can play with gamma in order to tweak epsilon to be exactly 0 and reach probability 1. So this was the conclusion. I leave you with an exercise that is completely unrelated to the exam, so do it only if you want to play with. I find it very nice, and if you don't find it very nice, probably you have a piece of stone instead of a heart. But no, so the exercise is the following. So the exercise is the following. Suppose that you have an input x given by, as Pedro was saying before, x n minus 1, so n words this time. So these are, let's say, b bits words. Okay, and I mean you can work at this level very, let's say, high level. So I mean, yeah, and you have the promise that this guy is 2 to 1. So for each I exists a j different than I, such that xi is equal to xj. Okay? So you can show that classically, so classical, the complexity of this algorithm become O square root of n, not On as before, but become O square root of n. And so this is the, so, sorry, yeah, and you, sorry, yeah, and you want to find a pair, so your goal is to find a pair ij that satisfy this property. This is called, in jargon, a collision. You want to find one I and one j, such that xi and xj have the same value. So classically, as I said, the complexity is O square root of n. Quantum, using Grover, you can bring it down to O n to the power 1 over 3, doing Grover. Notice, and this is something that I wanted to do but then we went a bit slower. If you remove this premise, so you don't know that the input is 2 to 1, you just look for a pair, for a colliding pair. Classically, this goes to On, and Grover also become On. So you cannot use any more Grover to solve this problem, and you have to go to the more advanced quantum random walk that allow you to go to On to the 2 over 3, such that you get an extra advantage again. But this is way, I mean, if you are curious about it, you can read the lecture 4 that we didn't do, but is in the website. And in principle, this is, if you want, up to here is problem, no, up to here in principle is doable. And also up to here. This part was problem 18 if we were doing the lecture 4. But again, this is completely unrelated to whatever will be in the exam, so do it only if you are interested in, and then we can chat, or you can, I mean, it's something that is easy to find. Okay, stop here.
Questions?
Yes, I think that the final conclusion is that the fact that these functions that we wrote are orthogonal allow us to...
the states, you mean?
The states.
Yeah?
Allow us to measure the rest
Yes,
of
allow,
of
if
the
you want, the
output.
fact that they are orthogonal, they live in a two-dimensional space, right? And so they allow you, well, you can, I don't know if they were, well, no, if they're not orthogonal, maybe you can try to orthogonalize them. But yeah, let's say the fact that they are orthogonal allow you to perform these rotations and go, yeah, if you want, if they are not orthogonal, when you are parallel to G, you still have a component along B. So the magic is that when you become parallel to G, you have zero component over B. This is a property of orthonormal things. So I would say if they're not orthogonal, you have perhaps a small but a non-vanishing probability to go badly. It's like, if you want here, suppose that you don't find this nice decomposition and you have to, for reasons, you have to bring this guy here. Now being parallel to G implies that you have something along B. So that, yeah.
Okay, understand. Thanks.
Okay.
Questions?
They need to have the lunch.
No, let's wait a few seconds.
Eh?
Let's wait a few seconds.
Say again? Yeah, essentially, as I said, you can implement this and you end up with the PK bar that now, which is, okay, I erased, correct. So PK bar that now is a function of epsilon, but is a function also of gamma. And okay, the only check that you have to do is that you can solve, it's actually a function of cos gamma. So you can, the only extra check is that you have to be sure that the required value of cos gamma is smaller than 1. Otherwise, you cannot achieve. But you get, I think you get an equation of the form cos gamma 1 plus something that involve epsilon equal to 1. And so this is telling you that, let's say, this divided by this is smaller than 1, and so it's solvable. And so so at the end, you tweak your A, deciding the value of gamma that make this to happen, and then you're sure that after k bar iteration, you have exactly the probability 1.
Can I ask a naive question?
Yeah.
So, as you said, you could replace x instead of 0, 1 to be a word.
Yes.
And xi equal 1 by f of xi equal 1.
I would say
That's
yes.
Easy. But f of xi should be implementable by quantum gates, right? If it's classical, no. Then it doesn't work, right? If I need a classical computer to compute f of xi, then no. Then I could not change this, right? I cannot call a classical computer. That's impossible.
I think that to call a classical computer, you have to measure, and so you're screwed.
Destroyed, right?
Yes, I think the best, but again, as we did in lecture 2, any classical function is implementable at the quantum level, so without...
No, I'm thinking about like something complicated that you will never do. I don't know. If f of x is 1, if that word appears more on one website versus another. I don't know, something like that. You are never going to code this.
I think any Boolean function, I mean, probably it's very contrived, but probably you can find a way to...
Okay, maybe a related question. In practice, when do people want to apply this? Is this going to be...
Well, I think maybe better to discuss when we're not recorded, right? So I think it's not, I mean, I think it's not going to be anything soon, because this is the usual thing, right? The coherence, noise, errors, so...
Because small n equal 10,
it's probably not convenient. It's
that's
much more
1,000. That's too little, right? We don't care about anything.
I would say yes. So
small n equal 20, it's already good?
Maybe small n equal 20, but then, I don't know, I'm not an experimentalist, but probably the noise that you start to generate in this circuit is so bad that at the end it's almost like tossing a coin. So I don't know. I don't know how much close we are to a use of this. Also because, fortunately, classical computers are going fast. So whenever we're going closer to use them, classical computers are so fast that put beyond. So
okay, so
yeah.
if it's not exponential, there's no.
No. I don't know, maybe in the future when we will have, when we and if we will have quantum computer which will be not prone to errors, not decoherent and so on, maybe. Square root is great, but the point is that the square root it's on paper. I don't think you can reach it right now.
Very good. Let's thank Dario once more.